Today we're going to talk about constraint satisfaction problems. So this is actually chapter 5 of the textbook. We're going to deviate just slightly from the order in the textbook, and the reason is we're going to need this material for the first assignment. Okay, so we're going to talk about constraint satisfaction problems. We're going to look at some examples of different CSPs, and we're going to start by looking at the simplest way of solving these problems, which is backtracking search. And then we're going to look at various enhancements to backtracking search to make it faster and more efficient. And finally, we're going to look at an alternative approach to CSPs, which is called local search, either hill climbing or simulated annealing. So this is the definition of a constraint satisfaction problem from the textbook. It's a set of variables xi, each with a domain di of possible values, and a set of constraints c. And the aim is to find an assignment of the variables xi from the domains di in such a way that none of the constraints are violated. And when you look at this definition, you may say, well, this just looks like a lot of mathematical mumbo jumbo, but I think if we look at some concrete examples, we'll understand better what's going on. So here's a simple example. We've got a map of Australia with 6 different states, 7 different states, and we want to colour this map with 3 colours, red, green and blue, in such a way that any 2 neighbouring regions are not allowed to have the same colour. So for example, Western Australia and the Northern Territory are not allowed to be the same colour. So here's a possible solution that doesn't violate any of the constraints. Now I should mention here, in this particular case we're using 3 colours, but there's a very famous theorem in mathematics called the 4-colour theorem, and that theorem states that any map, no matter how complicated a map you draw, it's always possible to colour that map with 4 colours in such a way that no 2 neighbouring regions have the same colour. And this theorem has a very long history. It was proven in 1976 by Apple and Harkin. So when I was a really little kid, 5 years old, my father used to tell me about this wasn't a theorem in those days, it was a famous unsolved conjecture. My brother and I used to have great fun drawing maps and seeing whether they could be coloured with 4 colours, and finally this proof was announced in 1976 by Apple and Harkin. And the way they proved it is, they said, okay, let's assume to the contrary that there's some map which can't be coloured with 4 colours, and so then they use various reduction techniques and say, okay, well, we break it down to what's the minimum map, what's the smallest map that has that property, and then it reduces to some few thousand special cases, and all of those cases have to be checked individually, and it's too tedious and time-consuming for a human to do it, so they wrote a computer program to go through and check all these cases. And so it was actually the first time that a mathematical proof was published, and in the proof it says, well, here's the program that we wrote, here's the code, we ran it, and this was the output it produced. Now, it seems funny to us, it seems very quaint to us from this long passage of time, because this has become so routine for such a long time now, but in fact, at the time it was very controversial. People were like, oh, you really trust the computer? And what if there's a bug in the program? What if there's a mistake? What if there's a flaw in the hardware? How do we know it's produced the right answer? And so there was a lot of philosophical controversy over that, and perhaps related, there was a lot of other controversy. People complained and said, oh, these guys haven't considered all cases, and there's certain cases they haven't considered. And these guys came back and said, no, you misinterpreted how we're counting, this fits into this, and blah, blah, blah. This controversy really went on until 1989. And I actually heard a first-hand account from someone who was at one of the conferences where this was discussed, and allegedly one of these guys was giving a talk and defending the validity of their proof, and one of their critics in the audience kept interrupting and saying, no, you haven't considered this case, you haven't considered that case. And eventually the guy speaking became so agitated that he actually rolled up his sleeves and came down off the podium and was about to hit this guy. Security had to be called to break up the fight. So I was very impressed when I heard about this, because You don't normally expect to see such excitement in the math. Here's another example, n queens problem. So the standard case would be a normal chessboard 8 by 8, but it can be extended to any n by n. And the idea is you have to put n queens, you have to put n queens onto the chessboard in such a way that no two queens are attacking each other. So no two queens on the same row, no two queens on the same column, and no two queens on the same diagonal if you go through all the diagonals. So if we wanted to formalize this problem, how do we do it? Well, the variables could be Q1, Q2. So we're sort of using domain knowledge in a way here to simplify the problem, because we're saying, okay, well, we know there has to be exactly one queen on each column. So we're not even going to consider a situation with two queens on a column. We're just, the variables will actually be whatever row those queens are in. So Q1 is the row of the queen on column 1, and so on. So the domains is just these row numbers. And what are the constraints? Well, we can't have two queens on the same row, so Qi is not equal to Qj when I is not equal to j. And then the diagonal constraint can be written like this to show that the two queens are not attacking each other. There's also these Crypt arithmetic puzzles that you sometimes see in the Sunday newspaper. So what happens here is every one of these letters corresponds to a digit. You've got to assign these digits to those letters, and it has to be such that this 4-digit number plus that 4-digit number gives that 5-digit number, right? So first of all, they have to really be 4- and 5-digit numbers. That means they're not allowed to begin with 0. M and S are not allowed to be 0. And then the fact that one number, some of the two numbers has to add up to the other number can be encoded in these constraints. But there can sometimes be a carryover, right? So when you add D and E, you either get Y or you get Y plus 10, and so on. And then there's a constraint that they all have to be distinct. So D is not equal to E, D is not equal to M, etc. Now this is a wonderful picture of Alan Newell, who was one of the founders of artificial intelligence. He and Herb Simon showed up at the 1956 Dartmouth conference with their logic theorist program, and he later developed a production system model of intelligence called SOAR, S-O-A-R, and he wrote a book about it called The Unified Theories of Cognition. And by the way, his collaborator Herb Simon, he wrote this book, The Sciences of the Artificial, which I also highly recommend. But he apparently loved this send more money puzzle. You can see send more money here written on the blackboard. Now we talked about the carryovers. Sometimes you can introduce hidden variables into the problem apart from the ones you were originally given. So in this case, there's a carry potentially from here to here, here to here, and here to here. So we've actually added those as extra variables. And then, you know, x1 is the carry, so O plus O is going to be equal to R plus 10 times x1. And then we would have W1 plus W1 plus x1 is equal to U plus 10 times x2, etc. So this is an interesting approach. Now, does it make the problem easier or harder? Well, the answer, and this is the case in a lot of these constraint satisfaction problems and methods, it really depends on the task. You've simplified the problem in a way, but complicated it in another way. Well, you've complicated it by adding additional variables that you didn't have before, but you've simplified it by adding additional constraints which guide the search. You eventually just have to use your intuition or implement it both ways and check which is faster. Here's another constraint satisfaction problem you're probably all familiar with, right? Sudoku. You have to put, what's the rule with Sudoku?
Put the numbers 1 to 9 in each box, row, and column.
That's right. So each one of these boxes has the numbers 1 to 9 have to occur exactly once in each box, in each row, and in each column. Okay, so all of these are kind of fun and games, kind of toy problems in a way. What about in the real world? Well, a lot of these problems do occur in real world situations. So there's assignment problems, who teaches what class, or in a hospital, which nurses are going to work which shift. There's timetabling problems, which class is going to be offered when and where. So a few years ago I was on a university-wide timetabling committee, and we had to discuss all these different issues about how we were going to make the timetable. There's hardware configuration. You want to lay out components on a chip in such a way that you minimize the total amount of wiring and the distance between critical components. There's transport scheduling. So a friend of mine years ago did some consulting work for the Greyhound bus company, trying to come up with a more efficient schedule for their buses. And you get a lot of different kinds of constraints with these sort of problems. So with the Greyhound example, the state of Michigan gave some money to Greyhound for them to buy buses. But those buses had to stay within Michigan. They weren't allowed to travel to any other state. And then there were certain other buses which were allowed to cross state boundaries, but were only allowed to travel between certain cities. So and then as well, you've got the constraints that a bus driver can only drive a certain amount of time, and then he has to take a break, etc., etc. So these constraints can be quite complicated. And then there's job shop scheduling in factories. You've got a factory that can be reconfigured to make different kinds of products, and you want to organize it in such a way that you maximize your profit. And what kind of constraints can we have? Well, constraint that involves only one variable is called a unary constraint, so m not equal to 0. If it involves two variables, it's called a binary constraint, and if it involves three or more variables, it's called a higher order constraint. These ones all involve discrete variables, but sometimes we have continuous variables, like in job shop scheduling. It may take 5 minutes to reconfigure a machine for a new task, so you might say, well, the third job can't start until at least 5 minutes after the first job has ended, and so on. So then you've got choosing continuously what time one job's going to finish, another one will start. And then you've got soft constraints or preferences where it's not absolutely necessary, but it's preferred. And I have to tell you, it was a fascinating experience serving on this university-wide timetabling committee and looking at the preferences of people from different faculties, right? So in computer science, we were concerned, we wanted to have the biggest theatres that we could have. We were prepared to teach at any time almost, but we wanted to have big theatres and comfortable theatres, right? Now, the law people, they didn't want to have to leave their own building. They wanted to teach only in lecture theatres that were within their own law building. You know, they were absolutely, you mean I have to walk outside the building and walk somewhere else on campus to give a lecture? I'd rather die. And then the arts people, they didn't mind what rooms they were assigned. Their concern was, I don't want to teach on Friday. That was the only thing they cared about. No Friday, right? And interestingly, the chemical engineering people actually had a preference to teach at 8 a.m. They wanted to teach at 8 a.m. We're like, fine, you can have any lecture, any theatre you want, that's fine. So very interesting little cultural differences. This is another constraint satisfaction problem. This is a little puzzle that involves dice, and every die is painted, there's 4 of them, and everyone's painted with 4 colours, red, white, green and blue. Okay? And the object of this puzzle is, you have to, if you put all the dice one on top of another like this, you can make a little a little tower, and you're supposed to do it in such a way that every as you turn the tower around, every colour should appear exactly once on every face. So you see on this face I've got blue, red, green and white. On this face I've got red, white, blue and green. This, oh that's interesting, yeah, on that face the same. So here I've only got one violation. Here I've got two whites and no green. Okay, so so you can think about, so in this case what would be the variables and what would be the domains? Well, the variables are the cubes, and then how many options have I got, how many choices have I got for each cube? Six?
3 for the first one.
Sorry?
3 for the first one?
3 for, yeah, good, okay, 3 for the first one, that's right, 3 for the first one. Now once I put the first one, how many choices do I have for the next one? Have a think about it. Yeah, I think it might be a little bit more than 6. In any case, you can see how you might, and this is true with a lot of these puzzles, this is sort of one way you might naturally approach this kind of problem. That you put one of them down and then you put another one down, and you try to put the next one down in such a way that it doesn't violate any constraints, and then you try the next one, and if you can't get this one to not violate any constraints, then you take it off and change this one, and so on. So this is what's going to be called backtracking search. And this is a nice puzzle because here we've got 4 cubes and 4 colours, but we can easily scale this up the same way as the queens. You know, we can have n cubes and n colours, and it just gradually becomes harder and harder as n increases. So how does this work? So initially we have nothing, just an empty state, and then we pick one variable that hasn't yet been assigned, and we assign a value to that variable. And then we take another one and assign that one in such a way that it doesn't cause any conflicts with the existing, already assigned variable. And if we can't find any assignment to that last variable, then we remove it and change the previous one. So this naturally leads to a depth-first search. Now the variable assignments are commutative. So in the case of the dice, it doesn't matter which die is on top of which other die. You know, as long as each die is in the same configuration, I can move them like this or like this. That's considered to be the same solution, the same state, right? And the same thing with the map colouring. If I colour Western Australia red and then colour the Northern Territory green, it's the same thing as if I did the Northern Territory first and then Western Australia is the same outcome. So we just consider an assignment to a single variable at each node in the normal case, and this is called backtracking search. So here's an example of how it would work with the map colouring. We just decide to start with Western Australia. We can colour that either red, green or blue. And then we might pick the Northern Territory next. That can be either green or blue. And then we move on to Queensland. That can be either red or blue, and so on. Now, an important thing to notice is, I'm going to assume you all know about depth first search because of this you've done this 2911 or you're doing it. The important thing to notice though is that in different branches of the tree you could assign the variables in a different order. So in this branch I've assigned Western Australia and then done Northern Territory next. Over here I could decide to do New South Wales next. So you could choose a different ordering for the variables as you go down different branches of the tree. And so you always try to choose the next variable in the way that hopefully will make the search more efficient. Right, so how can we sensibly make those decisions? How can we decide which variable to assign next? How can we choose the order in which to try the values? And can we detect early on that this branch is definitely going to fail and then save ourselves some time by pruning that branch? Now, to some extent it varies from one domain to another, but fortunately there are certain general principles for doing this which can apply to many different domains. So, well, let's think about this. Okay, let's say you pick Western Australia first and I colour it red. What would be a good choice for the next thing to try? Should I try Queensland? Should I try Tasmania? Should I try the Northern Territory? Which one do you think would be best? Northern Territory. Why?
Because it's adjacent.
Sorry?
Because it's adjacent to the color.
Adjacent to the, right, it's adjacent to the colour you've already filled in. That's right. So being adjacent means that it's it's constrained by the, yep.
Couldn't South Australia actually be a bit better?
Very good. Okay. Or South Australia might be even better, right? But the ones that are adjoining would definitely be better than the other ones. Okay, but tell me why South Australia would be better.
If you colour South Australia, you limit the number of variables on all other states except Tasmania. Your South Australia touches more states.
Very good. Very good. Okay. So we're just, so these general rules are actually really just capturing the intuition you already have about these puzzles. So the first heuristic is called minimum remaining values. Okay, so we choose, it's best to choose the variable which has the fewest remaining legal values. So after I've coloured Western Australia, there are still 3 possible choices for these ones, but there's only 2 possibilities for these. So that's why it's better to choose either Northern Territory or South Australia. Okay, so what if you've got several ones to choose from that all have the same number of remaining values? Well, then this thing called the degree heuristic can be used to further refine the choice. So, as you were saying, it's actually, in this case, probably better to choose South Australia because it imposes more constraints on these other states. Right? So here's another example. Let's suppose I happen to start with by colouring South Australia, then I'd be better off to choose Northern Territory, Queensland or New South Wales because they impose a constraint on 2 neighbouring states, whereas if I choose Western Australia it only imposes just a constraint here. That was to choose which variable to assign next. Okay, but now there's the question, okay, what value should I assign to that variable? So I've assigned WA and the Northern Territory. I'm going to do Queensland next. I can choose either red or blue. Which one would be better? Who says red? Who says blue? Why red?
South Australia.
South Australia, yeah. So if I choose blue, I'm imposing additional constraints on South Australia that weren't there before, that it can't be blue. If I choose red, well, I'm just imposing a constraint that was already there. So we try to pick the value that imposes the fewest constraints on the remaining variables. Now this is actually a degenerate case, or it's a special case because blue actually leaves no possible value for South Australia, right? So blue is going to leave, this is detecting failure earlier in a case, so definitely you would want that one. But the idea is this principle applies more generally. So let's suppose this were part of a larger map. Let's say I'm not just colouring Australia, I'm colouring the whole world, but I want to do it with 4 colours instead of 3. Well, I would still prefer this over this because this would leave me 2 choices and this would leave me 1 choice. So it's better to have 2 choices. Okay, so it's just a general principle. If you had 3 versus 2, then 3 would be better and so on. So you always pick the one that leaves open the largest number of options for the remaining variables. And by combining some of these heuristics, instead of 25 queens, we can solve up to 1,000 queens in a reasonable time. Okay, now how would you go about implementing something to make these choices? Well, one method of doing it is called forward checking. So you set up a data structure which keeps track of all the remaining legal values for unassigned variables. So the way this works, at the beginning, everything is legal. Okay? Any of those states could be any color. Now after we assign red to WA, we go along and say, okay, well the Northern Territory can no longer be red. Right? So we cross that off. South Australia can no longer be red. We cross that off, and this helps us to choose what to do next. So it means we possibly want to choose Northern Territory or South Australia because they've got few values, but somehow we've perversely chosen Queensland instead. But in doing so, we say, okay, well, Queensland is now green. That means the Northern Territory can't be green, and New South Wales can't be green, and or South Australia. And we keep going in this way. And then if we assign blue to Victoria, then it turns out that actually South Australia has no options remaining. So at this point, we can chop off the search and say, okay, we know that this is going to lead to failure, so there's no point pursuing it any further. Now, if we were smart, we could have perhaps detected even earlier that this was going to fail. Once we assigned WA and Queensland, is there any solution with those initial assignments?
No.
No, why not?
Because South Australia and Northern Territory have the same only legal value.
That's right. Yeah, exactly. So once we've covered this, the Northern Territory has to be blue, and South Australia also has to be blue, and they can't both be blue. Yeah, so we get used to doing this kind of thinking ahead and detecting things early when we solve Sudoku puzzles and that kind of thing. There's special books about Sudoku, special techniques for detecting early failure. But it's an interesting question. Well, okay, how can we take that intuition and encode it into a computer program? And we can do it by something called constraint propagation. And the simplest form of constraint propagation is called arc consistency. So the way this works is we start comparing things pairwise that have constraints with each other, and we say, okay, the remaining values for x to y are consistent if every value of x leaves open some value for y. So how does this work? Well, let's look at South Australia and New South Wales. Well, if South Australia is blue, then New South Wales can't also be blue. Okay, so we cross that out. So that thing is excluded. And then we can say, all right, well, what about Victoria and New South Wales? Well, if New South Wales has to be red, so that means Victoria is not allowed to be red. And finally, we end up looking at Northern Territory and South Australia. Now, as a human, we didn't bother with all this stuff. We just looked directly at the Northern Territory and South Australia. Right? But the computer's not quite that smart. It just starts checking everything pairwise. And it says, okay, well, since the Northern Territory has to be blue, that means South Australia can't be blue. So that means the thing's going to fail. Right? So we can do this either as pre-processing at the beginning, just to kind of direct the search as an initial stage, or we can update this every time we do a variable assignment. Now, I have to say, every year there are some students who are not happy with this. They look at this and they think, well, I can't see how this could possibly speed up the search, because isn't it just doing really the same as what backtracking search would do, but doing it in a different way? And the answer is, well, that's true to some extent, but it really depends on the problem. So there are some problems for which this technique doesn't really help you at all, and in fact it may slow the search down because you're implementing extra data structures. Every time you do an assignment, you're doing this extra processing to check for these inconsistencies and so on. There may be some tasks for which the computational overheads of doing all that actually makes the thing slower than what it would have been otherwise. But there are some problems for which this actually speeds the thing up enormously. And the best way I can explain, first of all, you have to think, this is just a very small problem, but you have to think in the large. You know, let's suppose I have 1,000 variables to assign, and there's lots and lots of constraints, and so there may be 5 different groups of variables that are likely to cause a conflict. And if I was doing backtracking search, I would have to pick one group first and search down there, and then pick another group and search further and search further. So I'd have to do them in some order. This process, if, in a sense, like examines 2 things. It focuses attention on the pairs that are likely to cause conflicts, and it somehow gives you some implicit parallelization. But actually, in effect, what you're doing is searching those 5 different groups of constraints in parallel without actually building the entire tree to do it. So, any questions about this?